everyone. Welcome to today's class. Today we'll start to talk about data visualization. We will use about 2.5 lectures to talk about this topic. And the first session is about the underlying theories about data visualization, sort of somehow new theories about it. And then in the next few lectures, we will talk about, in particular, a package called ggplot2. And we will use ggplot2 to create different types of visualizations for different types of data and different combinations of data types. Okay, all right, let's start from the very beginning. So we are done with introduction to data science and our basics. So we are here, data visualization. The first session is about composing and dissecting data graphics. So there is a taxonomy for data graphics. There are 4 basic elements: visual cues, coordinate system, scale, and context. And Hadley Wickham, who is the author of ggplot2, the ggplot2 package, implemented these 4 elements when he created the package. We will see in a moment. So let's take a look at each component or each element in a graphical display one by one. So first, visual cues. So this plot shows you a big picture of different visual cues: position, length, angle, direction, shapes, area, volume, color saturation, and color hue. And definitely they are used to visualize different types of data and different number of variables as well. So for example, length can be used to measure one-dimensional quantitative data, and area can be used to measure two-dimensional quantitative variables, and volume three-dimensional. So these are all about magnitudes, right? And angle is similar to length, right? But it can be used to demonstrate numeric variables too, but it is in a different coordinate system, a polar system. And then there are some visual cues that can be used to illustrate relationships between variables. For example, position and direction can be used to show relationships between 2 variables. And some variables can be used to illustrate, to display numeric variables and categorical variables. For example, color saturation, right? You can use it to show continuous numeric variables. Sometimes you can also use it to show categorical variables. Okay? And lastly, shapes and color hues are usually used to display categorical variables. Okay? So the purpose is to make contrast between categories, right? So let's take a look at them one by one. So first, length. So length is used to show one-dimensional quantitative variables. But just pay attention, sometimes people can mislead you using very smart tricks. For example, so this graphical, the first plot shows you, so this is a bar plot. Now in January 2013, you have the some percentages shown. So first one is 35%, the second one is about 40%. But notice that in the first plot, the y-axis starts at 34%. And consequently, you see it exaggerated the difference between the two bars, okay, the height of the two bars. If you start the y-axis at 0%, then you see the difference is much smaller, right? Much smaller. So sometimes you can mislead people, but as a professional data scientist, we should never do that. Okay? We should be honest and um, try to show the data in its original way. Angles can also be used to show one-dimensional numeric variables. So, for example, in a pie chart, we use angle to show the size of each category, okay? Each the percentage somehow like that. Okay, so this is like 25%, 50%, etc. Donut plots are similar to pie charts. Instead of using angles, it uses arcs to show the magnitude. But essentially, because the arcs are related to the angle, the size of the angles, directly related to the angles. So essentially, they are the same thing. They are using the angles to show the magnitude. Okay. And next, two-dimensional area. Three-dimensional numeric data, you can use volume. Okay. However, you see that just compare these two. Okay. So the first square is representing a unique square. Right? So the magnitude is 1. Then the second is 2 by 2, 2 times 2. So it represents 4. Okay. And similarly, at the bottom, the first one is a unit cube. Right? The second one is a cube that represents 4 times of the previous cube. The volume is 4 times of the previous one. Okay? So you can tell very obviously the difference between these two is more obvious than the difference between these two cubes. Okay? And if you compare length of two segments that represent 1 and 4, so you see the difference is even bigger. Okay? So from these three examples, it's very obvious that one-dimensional measurement like length is the most effective. The three-dimensional one is the least effective. So whenever it's possible, just directly use length instead of using area or volume to show one-dimensional data or quantitative variables. And then the next visual cue is position. Position is used to show relationships between two quantitative variables, usually quantitative. Sometimes you can show the relationship between one quantitative and one qualitative. Okay, it's very rare. For example, in a scatter plot, we can use position to show the trend, the relationship. So the first one is apparently a linear relationship, positive. And the second one is a negative linear relationship. You can also use positions to show clustering within observations relationship, right? Cluster 1, 2, and 3, right? And you can also identify outliers. Outliers are observations that are far away from most of the data points. Right? So obviously this is an outlier. Okay? So position is used to show relationship. Okay? And next one is direction. So sometimes you want to create a line plot somehow to show the trend. Usually it is using a time series plot. Okay? So for example, in this plot, you can see a clear upward trend from 1960 to 2000. direction. And then shape. Shapes are used to display categorical variables usually. Okay, we use different shapes to demonstrate different categories. For example, square, circle, triangle. Okay. And next group is shade and color. Okay. Color saturation is the shade, and color hue is also called color itself. Okay. So colors are very flexible. You can use colors to display categorical variables. Sometimes you can also use colors to display numeric variables, quantitative variables. For example, in this graphical display, it shows estimated fraction of precipitation lost to some reason from 1971 to 2000. So each unit is probably a county. And the author used, I think it is a rainbow color palette to show a numerical variable, which is fraction of precipitation loss. Okay. So from this plot, you see that it probably is not a good idea because you see 0 to 0.09 is white, and then goes to pink, dark pink, and purple, and aqua blue and blue, etc. So there is no pattern. Okay? So it's kind of like at least from the lightest to the darkest, there's no such kind of pattern in between the colors. So choosing the rainbow palette is not a good idea in this case. Okay? So actually, maybe choosing one color and using different shades or color saturations of the same color to demonstrate this numerical variable is a better idea. Okay? So that you can clearly see the change and the relative relationship between counties, among counties. Okay? So we need to be careful. Okay? And there are some color blind safe palettes available for us. So this person, Cynthia Brewer, created these palettes for colorblind safe palettes. So you just need to install this package called R-Color Brewer. There are three groups of colors. First one is sequential. So the ordering of the data has only one direction. So basically, in this palette, for each color palette, there is only one color, almost one. Okay? Maybe it's gradually change a little bit. Okay? So it's good to show continuous numerical variables or discrete numeric variables. Okay? As long as it's kind of there is an ordering, there is an order among the numbers. So sequential, good for quantitative data. And the second group is a qualitative group. So see set 1, set 2, set 3. So see there is no continuity between the colors next to each other. That is because these color palettes are good for categorical variables. Right? The purpose is to show contrast, to compare different categories. Right? So the more difference, the better. So that's why they are not continuous. Right? And the last palette, the last group is diverging palettes. So they are good to show the ordering of data when data has two directions. For example, the presidential election data, you can use red to represent Republican and blue to represent Democratic. And then you can allow overlapping areas, which will be purple, okay? But in this case, the middle area, the battleground will be shown as like white, okay, somehow. But anyway, is diverging to do two directions. So these are all available for us as long as we install this package, our color bluer. Okay? Very pretty colors, and they are colorblind safe, which is really good. And we talked about a lot of visual cues. So which ones are more effective, which ones are less effective. So we actually have compared length, area, and volume already. They are in this order. If we have to put them all together, then position is the most effective, and color hue is the least effective. But of course, this comparison is not a very fair comparison because some color hues are for categorical variables, some are for numerical variables, some are used for two variables, right? Some are used for one variables. So not a very fair comparison, but this is just um, a rough ordering, okay? And this also shows you the effectiveness of color hue, visual hues. The first column lists the visual cues for magnitude channels or ordered attributes. So if your data is quantitative or categorical but ordered, okay, ordinal data, then you can use these visual cues. So still, position is the most effective, and then position on unaligned scale, then length, angle, area, depth. Depth is the third dimension. So it's demonstrate the volume actually. And then color luminance or color saturation. And then, yeah. Anyway, so sometimes people use different terms on the same thing. And curvature and volume. And for categorical attributes, the most efficient one is spatial region, and then color hue, etc. We just need to have an idea about the relative effectiveness of these visual cues. We don't have to be very rigid. We have to pick the most effective one. Always, we don't have to do so. We can be very flexible. All right. We're done with the first element, visual cues. Then the second element is coordinate systems. So roughly speaking, there are three coordinate systems: the Cartesian system, polar system, and geographic system, map system. For Cartesian system, we have two coordinates, x and y. So this one is a Cartesian system. And for any observation, you need to specify two coordinates. And in the polar system, we also need two coordinates, but they are r and theta. R is the radius, and theta is the angle. So for example, for any points in the polar system, we use two numbers to denote it. One is r, the other is theta. R is the radius, and theta is the angle. So there is a one-to-one correspondence between a point in the Cartesian system and a point in the polar system if both variables are quantitative. But sometimes, pay attention, you may use categorical variables in a Cartesian system. It's okay, it's totally fine. Right? Or even, usually one categorical variable. For example, in a bar graph, the x variable most likely is a categorical variable. The y variable may be a numerical variable. And last one is geographic system. The coordinates are the latitude and the longitude. So usually it is just for creating maps So because, a map is a two-dimensional projection of a three-dimensional object. Our Earth is a ball. If you force to project it to a two-dimensional plane, then there must be some kind of distortion. So a geometric coordinate system will try to minimize this kind of distortion or complement this kind of distortion so that it will reflect the true look of the Earth, the surface of the Earth. Okay, so that's why whenever you draw a map, try to use a geometric system instead of a flat Cartesian system. All right, next element is scale. So scales translate values into visual cues, and the choice is often very crucial. So we will briefly introduce a few scales that we commonly use in data science. The first one is numeric. So this is the most commonly used one. So it's used to measure numeric variables. There are different types of numeric scales. Linear is the most common one. And then we also have logarithmic, percentage, etc. And time is also a numeric quantity, but it has some special properties. So first of all, because of the calendar, it can be separated by a series of different units. For example, year, month, day, hour, minute, second, even smaller units. And secondly, it can be considered periodically as a wraparound scale. It's just like a clock. It repeats itself. It's periodic. So time is a special numeric scale, but because it's very special, we just call it a time scale. And the last one is categorical scale. For categorical variables, we need to use categorical scales. And there are two types of categorical variables, right? We have nominal categorical variables, and we also have ordinal categorical variables. For nominal categorical variables, there is no intrinsic order among the categories. So in this case, it doesn't matter how you order the categories on the axis. It doesn't matter. But for ordinal, for example, you have a variable which is used to measure the smoking status. There are 3 levels: never, former, and current smoker. Right? So apparently, in terms of the influence on a person's health situation, these 3 categories are ordered. And never, maybe no influence, definitely no influence. Right? And former, potentially some influence, and current smoker, ongoing influence. Okay? So clearly these 3 levels are ordered. So that's why it's called ordinal data, ordinal variable. In this case, you need to order them in the correct order when you put the values in the axis, in one axis of the graphical display. Okay. All right, let's take a look at them in more details. So scale. So this part shows you 6 commonly used scales. Linear, right? In a linear system, so the increase of the values are linear, right? 0, 1, 2, 3, 4, right? And then logarithmic. So this one is also a numeric scale, but instead of increasing the values linearly, the values are increased exponentially. So notice that 0 is what? 1 is 10 to the 0. Right? 10 is 10 to the 1. 100 is 10 squared, etc. So the values are increased exponentially. Right? And logarithmic scales are good for data with a lot of outliers on the right-hand side of the coordinate system. For example, if the data looks like this, right-skewed, a lot of outliers on the right, then it makes sense to use logarithmic scale because if you take log of some positive values, then small values, relatively small values, values between 0 and 1, will be exaggerated in terms of magnitude, although they will be transformed to negative values, like log x. If x is less than 1, it will be negative, but the magnitude will be enlarged. Okay, but for big values, like somewhere here, if you take log, they will be compressed to smaller magnitudes, smaller regions. So consequently, overall, it will be less skewed if you take log of your data. Similarly, if you use a logarithmic scale, the data will look like more, it will be less skewed and more symmetric. And so this one is numeric, logarithmic is numeric, and also percent is numeric. By the way, logarithmic scale is commonly used earthquake strength, sound loudness, light intensity, pH of solution, etc. As long as the data is just right skewed, with a lot of outliers on the right-hand side, it's good to use logarithmic scale. And the data itself should be positive. Otherwise, you cannot use log scale. And then categorical scales, categorical and ordinal. So if there are no intrinsic order, you use a regular categorical scale. If there are intrinsic order, for example, small, larger. So see horrible, bad, okay, good, great. They are. There is an ordering among the categories, then you should put them in order. And then last one is time. January, February. So this is corresponding to months. You should order them according to the time order instead of following the alphabetic order, right? And also this part shows you the periodic feature of time. Time in a day, week, days of a week, and months, and then seasons, right? So all of these are time scales. And finally, this one shows you a bar graph. So in a graphical display, you can use different scales on different axes. You don't have to use the same scale on all the axes, of course. It's quite flexible. All right, the next slide shows you the importance of choosing an appropriate scale. So all of these 6 maps or graphs are using the same data set. Roughly speaking, the same data set. But if you manipulate the data or you transform the data differently, you will see completely different graphs, right? So the first one you see, it uses quartiles. So the variable is percent with at least bachelor's degree in 2009 percent. So the unit in the data set is a state, apparently, including DC, I think. So 51 units, 51 observations. And then it actually cut the variable into 4 categories using the quartiles of data. So Q1, the median, and Q3. So Q1, by definition, is the value such that 25% observations are less than or equal to Q1, the value, right? And then median is the midpoint. Right? In Q3, 75% of observations are below this final or the maximum. Okay, so totally, so the data is categorized into 4 small intervals and then use different color saturations to demonstrate the 4 categories. So this is important. And this one is linear. They just use 15%, 20%, 25% as threshold. And this one only measure the mean. So see, if you use different standard, different scale, you can see different, totally different graphs. All right, last one is context. So a visualization is not only about the look of the plot or graph. It's necessary to add some context so that when people look at your plot, they understand what information you want to convey. Right? Titles, subtitles, very important. Captions, sometimes important. For example, usually you provide data source in the caption part, and then axis labels, very important. Right? Your readers need to know what these 2 axes are about. Right? And the last one, reference points or lines. So this is also important. Right? So very likely you will your plot will display grouped data. Then you need to provide a legend. You let people know which line is for group A, which line is for group B, for example. Right? So also very important. So these are items in context. Put them together, you see so different visual cues in different coordinate system can create different plots. For example, length. In a Cartesian system, it could be a bar graph or a histogram. You can also put it in the polar system and create a plot like this. I don't know what is the name of the plot, but I have seen this before. But to be honest, this is not a very effective way, right? Because it's difficult to compare a bar here and a bar here, right? They are not next to each other. And in a map, geographic system, length can be used to measure the distance. For example, the distance of a route, of an airline, of a flight. So a lot of possibilities. And the last slide is dissecting a plot. So given a plot, you should be able to dissect it. Namely, you decompose it into the 4 basic elements. So this is a way to train yourself to truly understand a graphical display. For example, this is a bar graph, not a histogram. It's a bar graph. So each bar is corresponding to a month. So let's start from the beginning. Which visual cues are used in this plot? So apparently length is used. And color is not important because all the bars have the same color. They use the same color. So color hue is not a visual cue. And coordinate system, apparently this is a Cartesian system. Right? And scale, the X variable uses a time scale. The Y variable uses a linear numeric scale. You see numbers, units are increased linearly. And lastly, context. Let's identify the context provided. There is a title, a subtitle, and a caption, And there are no X and Y axis labels, but there are tick marks for in the X-axis and Y-axis, and also the units. So that's all. That's all. But I think it's enough. You don't have to add the axis label. For example, it's apparently time. You don't have to put months here. All right. And there are a few exercises at the end of the lecture, but we will skip them as usual. I hope that we can finish the first part of ggplot2 and then next time so that we have enough time for you to have a quiz on Thursday. Okay. All right. Do you have any questions? All right. So now let's move on to ggplot2, implementing the grammar of graphics using ggplot2. I suspect GG stands for grammar of graphics. Okay. All right. First, let's see packages that we will use in creating graphs, for creating graphs. So in our class, we actually will use many packages. The first package is called MDSR. It's Modern Data Science with R. This is the package associated with our textbook, the first textbook. So it's free. You can download and install it by yourself. It has some data sets that we will use in the future, in next module, and also this module. And tidyverse. So this is a package, and it is also a collection of packages. It contains most of the packages that we will use in our class. So if you click this link, you will be directed to this page. This is the web page for tidyverse. It contains a lot of packages, and among them, there are 9 core packages: dplyr, ggplot2, readr, etc. ggplot2 is used for visualization, dplyr is used for data wrangling, etc. And if you click packages, then you will be directed to here. So this one lists this web page shows you all the packages that are included in tidyverse. So there are 9 core packages, as I said. Core packages will be loaded whenever you load the tidyverse package. So they will be available for you. But there are some additional packages that are included in tidyverse. So as long as you install tidyverse, they are installed at the same time. But when you load tidyverse, those packages won't be loaded automatically for you. Those non-core packages. So let's take a look at the core packages. ggplot2 is the first one, and dplyr is used for data manipulation. tidyr is used to clean data, like change the format of data sets. readr contains some fast and friendly way of fast and effective functions to load data, to read data. And purr is used to work with functions and vectors in a consistent and fast way. And tibble, stringr. And the last one is used to deal with time, dates, etc. Lubricate. But in this module, we will focus on ggplot2. So I encourage you to install tidyverse directly so that all of these will be available for us to use. We will use almost all of them in our class. Go back to our lecture. So ggplot2 and dplyr are part of tidyverse. And then there is also a package called Mosaic. So this one has some data sets that we will use. Now let's focus on ggplot2. So this a package this is a package which implements the grammar of graphics. So basically, it considers the four elements of graphics: visual cues, coordinate systems, scale, and context. Okay. And a very helpful tool is the visualization cheat sheet. If you click this link, you'll be directed to somewhere here. The POSIX webpage about cheat sheets. I've shown you how to find the cheat sheet for R Markdown. For now, ggplot2. Click view the cheat sheet. You'll see the cheat sheet webpage. So if you want to download it, just click this one. You will download this PDF version of it. Otherwise, you can just read the web page. Everything is enlarged. It's easier to explore to read because the letters are larger. Okay. All right, let's go back. So now so because this is the first class about ggplot2, I will explain everything in details. It seems very slow, but I think it's good to start in the right way so that you can avoid a lot of errors in the future. Okay? So we will follow examples in our second textbook, R for Data Science, the free book. Okay? And we will use a data set called MPG. So this one contains observations collected by the U.S. Environment Protection Agency on 38 models of car. So it's a very small data set called MPG, only 38 observations. So MPG is actually a TIBO. Okay? A TIBO is a special format of data frame. So let's first load the Mosaic package. I think MPG is built in Mosaic. Right? So I load the package and then check the class of MPG. This is a data set. Right? So there are three strings: TIBO, DF, TIBO, and data.frame. So it is a data frame, but it is not only a data frame, it's a TIBO. We will focus on tables a little later, but for now, you can treat it as a data frame, a two-dimensional data set. Let's first check the dimension of MPG, 234 rows and 11 columns. All right, sorry. I said 38 observations. That's not right because each model may have multiple cars and multiple rows about it. So totally 234 rows. Take a look at the first three rows of the data set. So I chose to print the first 6 columns and then the last 5 columns separately. That is because MPG is a TIBO. And by default, if you print a TIBO, it will only show the columns that can fit into the current screen, no matter how big it is. For example, because I generated a slide presentation, I separated into 2 parts. So this is narrow, and then it will only show a few columns. So that's why I separate. I use 2 head functions to show them separately. Let's take a look at the variables in the data set. Manufacturer of the car, model, displacement. So this one is engine displacement measured in liters. So this one is used to measure the size of the engine. And then year of manufacturer, cylinder is the number of cylinders, and type of transmission and type of drive, front wheel drive, rear wheel drive, and 4-wheel drive, right? 3 types, the categorical variable. And then city. So this is the city miles per gallon. apparently this is one of the response variables that is of interest. It's used to measure the fuel efficiency of a car. And we have a similar response variable called highway miles per gallon. So this is another measure of the efficiency. So we have two options. Right? We can also take average of them. But anyway, they are all available for us. And then fuel type and lastly, type of car. You see compact or minivan, etc. All right. Now, suppose we want to answer a question, a research question or a hypothesis. Do cars with big engines use more fuel than cars with small engines? Basically, we want to know if cars with big engines are less fuel efficient. Based on our common sense, it should be the case. The larger the car, the less efficient it is. We want to answer this question using a visualization only. So let's create a scatter plot to show the relationship between engine size and fuel efficiency. Of course, we have two options for the measure of fuel efficiency. We have city and highway. Suppose we just choose highway MPG. And X variable has to be this displacement. So this is the only one that we use to measure the engine size. Okay? And let's create a scatter plot. So we first load the package. As I said, if we load the tidyverse package, then all of the core packages will be loaded automatically, including ggplot2. If you don't want to load the gigantic package tidyverse, for now, you can just load ggplot2 directly. Let's put it here, ggplot2. And then let's see how to create the plot. So start with the ggplot function, parentheses, specify the data set, plus gm point. And then there is a mapping argument. X is equal to displacement, Y is equal to highway. Right? So let's first take a look at the plot. Okay, apparently, there is indeed a negative relationship between displacement and highway efficiency, which is expected. And then let's zoom in the code. So with ggplot2, you begin the plot with a function ggplot. So you always start with ggplot. Right? And then the ggplot function will create the coordinate system. So basically, it will not do anything else but create a coordinate system. By default, it is a Cartesian system. Right? Unless you change it at the end, you have the option to change it later, but by default, it's Cartesian system. And then the first argument and a necessary argument in ggplot is the data argument. You need to specify the data set you use to create the plot. Right? We use MPG. And then after this part, you have the option to add layers of visual cues to it. Okay, so that's why there is a plus here. So that means we are adding a layer of points into the Cartesian system, right? Coordinate system. So that's why you always connect with a plus. And gm point is used to add a layer of points. Right? GM stands for geometric object. GM points is used to create a scatter plot because it will add points to it. So yeah, GM stands for geometric objects, and ggplot2 provides a lot of options for geometric objects. For example, GM smooth will add a smooth curve like lowest local weighted regression curve to the system, and GM_bar will add bars to a system, right? And GM_polygon will add polygon histogram polygon to a plot, frequency polygon to a plot, right? And ggplot2 allows you to add multiple layers of visual cues into the same system. So namely, after you add a layer of point, you can continue plus, and then, for example, GM smooth, you can add a layer of a smooth curve to the point to show the pattern, right? So it's very flexible. This is the basic syntax of the ggplot function. Data equals some data set and plus, right? And some GM function. It depends on what visual cue you want to add to the system. You can choose a GM function. We use GM point. And then within the GM function, there must be a mapping argument, So this mapping argument is used to map your data to actual visual cues. In our previous example, you see we map displacement to the x-axis and highway to the y-axis. So namely, we map these two variables into the position of points. Okay? And notice that in the mapping argument, you have to wrap everything in AES, in the AES expression. AES stands for aesthetic. So basically, it's you use it to wrap all of the different pairs of mappings in it. And you have to start with it. You can omit this mapping equal to, actually, because this is the argument name. You can omit it. You can start with AES, but this AES cannot be omitted. Right? And so in the syntax, we actually can identify the 4 elements in graphical display. First, ggplot2, the ggplot function will open a coordinate system, right? And visual cue is used, visual cues are specified in the mapping part, right? And then scale is automatically chosen as appropriate as possible. So basically, there is a default scale for each coordinate system. So if you use a Cartesian system, and also, of course, it depends on how you map the x and y variables. Okay, so it will automatically choose an appropriate scale for you. And context is given by the axis labels. So by default, it will provide some context, but minimally. Basically, x and y axis labels will be provided, and no title, no subtitle automatically created for you. You need to add them by yourselves. And then let's add more. We can add more variables via visual cues. So from this plot, you see that there is a kind of linear, but not exactly linear pattern, right? So if you carefully examine it, you see that there is a kind of a curly relationship, right? So this part does not follow the pattern that well. Okay? So they are kind of like outliers. So in this case, you might suspect that some categorical variable plays a role in the relationship between displacement and highway efficiency. Right? So in this case, you can choose to map the categorical variable into a visual cue, for example, color or shape of points. So let's map class to color. So notice that I just add this argument within this AES expression because it is a mapping, right? It involves variables. So it's a mapping. We map class to color. So it has to be in the mapping. So if we do so, we quickly identify that these points all belong to one class, which is two-seaters. Which is intuitive because sports cars are usually have large engines because they are very fast, but at the same time, they are not so efficient. Right? So they have they are better than other large cars like minivans or else, but it is so they are kind of a special group. Right? So this one, so by mapping class to color, we figure out the reason. Right? So these are special. Now let's zoom in and talk about more details in the mapping and more options. For example, we can change the shape of the point. For example, we can choose, let shape be 22. 22 is a point like this. It's an empty square. Okay. And in this case, if we want to map class to color, we should let fill be class because we will actually specify the filling color of the point, shape 22, right? It's specified by fill. Right? If you use color, then the boundary of the point will be changed, but the inner part is still empty, it's white, right? It's transparent. So it really depends on the type of point you use. But by default, it is a solid round point. You can map class to color in that case. For solid points, you can map class to color. And notice that shape equals 22 is outside of AES. Okay. What's the difference between shape equals 22 and these three arguments? Can you tell?
Is it because shape is not referring to a variable in the data set?
Exactly. Thank you. That's correct. Right. So this one does not involve any variable. It's not mapping. It's not a mapping, right? So it should be outside of this AES expression, right? And it's a kind of a constant. You assign a constant value to an argument. It should be outside of the mapping argument. Great. And because we understand that, then we have more flexibility. For example, if we don't want to map class to color, we can just use the same type of points with this in the same color. Then we can, for example, specify shape equals 15. Then it's a solid point. Right? Shape is 15 solid point. And that color be blue. So again, this one is still mapping, changing color, but it does not include any mapping of variables. So it should be outside of AES, right? And size is used to control the size of the point. So this is just another example. And in our class, of course, we cannot demonstrate all of the possibilities in colors and other things, shapes. You can take a look at this website for different choices of colors. And also the our color brewer package has a lot of colors available for colorblind safe palettes we just talked about. So for each color, there are different ways to identify them or to define them. Right? There are hexagon code, like name code, number code, different things. And our last topic is adding more variables via facets. sometimes you think a categorical variable is very useful in explaining, in influencing the relationship between some other variables. In that case, you can choose to create subplots or facets according to the categories of a categorical variable. So this is one option. So previously, we mapped the class variable to color. So that is one option. The points are all together. Okay. However, if they overlap with each other a lot, it will be difficult to identify the pattern, especially if there are so many classes, so many categories. They all mix together. Okay. If you want to separate them, you can use facet. So ggplot2 provides two functions. The first one is facet wrap. If there is only one categorical variable that you want to add to create a subplot, we use facet wrap. So you can just add this facet wrap function at the end of your plot. So for to avoid repetitions, I first create a scatter plot, a very basic scatter plot with displacement and highway, the black point one. I call it G, assign it to G. Okay. And then I can take G and plus facet wrap to the class. So the grammar, the syntax is always like this. Okay. To the variable. That means I will create subplots corresponding to the categories of the variable to the X. So this is kind of like a formula. And you can optionally specify how many rows you want. If you don't specify it, the ggplot2 will choose the number of rows for you. Okay. Let's see. So this is the result. G is the original scatter plot, and we add facet wrap. So let's see for different classes. For each class, we have a small scatter plot. And the very good property is all of the facets share the same X and Y, X and Y axis labels, and also the tick marks. They are all shared with each other. So yeah, avoid repetitions. So then you can see the relationship between displacement and highway are kind of different for different classes of cars. For two-seaters, for example, almost no relationship. If you fit a regression line, probably it's horizontal, right? And for compact, you can observe the biggest slope, the negative slope, and mid-size minivan. So you can observe that there are different kind of relationship between X and Y for different classes, which means the class is indeed a very important factor in influencing the relationship. And if you have two variables, two categorical variables to group the data, then you can use facet grade. So the only argument you need is a formula in it. For example, a drive to the cylinder. So this means the rows are corresponding to categories of drive, and the columns of the entire plot are corresponding to the categories of cylinder. Cylinder has four categories, 4, 5, 6, and 8, and drive has 3. 4 wheel, front wheel, and rear. And then you have a grid of flats or facets. So some panels are empty because we only have 234 observations, a very small data set. Some of them don't have any observations. So this is an option. You can use FASIC grade to group the data using two categorical variables. You can also use FASIC grade for one categorical variable only. You just use this kind of syntax. Suppose you want to facet the plot into columns only. Then to the drive, put a period at the beginning. So this means no row variable. We only use a column variable. Alternatively, you can specify the row variable and omit the column variable. Then you will have a column of plots. It really depends on the shape that you prefer, right? Or the space that you have in your report or project or paper. Change the shape a bit. And lastly, you can also map a variable to color. So it's very flexible. You can add more variables into your plot. But usually we don't recommend you to add too many variables into a particular just one plot, because you want people to focus on the main information, the most important information, instead of being distracted by some trivial information, right? It better just focus on a few things. As long as you can tell the story, that'll be good. And another thing I want to emphasize is that the mapping argument can be moved to the ggplot part too. So in this class, we haven't talked about that yet because we only have one layer of visual cues. If we have multiple layers of visual cues, for example, a scatter plot, and then you overlay a linear regression line, right? Apparently, the points and the line share the same X and Y mappings. Right? Same thing. In this case, you can move this mapping part into this ggplot function part. Just remember you need to separate arguments by comma. So data, MPG, comma, mapping, blah, blah. So as long as you are sure that the two layers of visual cues share the same mapping, then you can put it in the ggplot part. In that case, this mapping will be a global mapping option for all of the layers after that, after all of the layers in the coordinate system. Okay. However, it doesn't mean that you cannot change it later. It's very flexible. Global options are available, and it defines all of the general options for all of the layers. However, in a particular layer, you can change it. You can add a local mapping argument, and it will override the global option, right? So the global option is the weakest, actually. Okay, it can be overwritten by local options. Okay? So it's quite flexible. And next time, we will see more examples. And today we'll continue to talk about ggplot2. So first, let's load the tidyverse package again. Okay, tidyverse is a collection of packages, including ggplot2, this package. So first, take a look at these two plots. So these two plots are using the same data set, the MPG data set, and exactly the same mapping. You see, the X and Y coordinates are exactly the same. Okay? However, they look very different, right? So the main difference is because they use different gems. Right? The first one use gem point, the second one use gem smooth. Right? So a gem is the geometric object that the plot uses to represent data. Okay, so if you choose to use different gem or geometric objects, you definitely will see different plots. The left one is a scatter plot. The right one shows you a smooth line, which uses local weighted regression model. So underlying the behind the screen, a model was fitted actually, and the result is a smooth curve. Okay. This band is a 95% confidence band for the mean response using this smoother. So as I said last time, ggplot2 provides a lot of different GMs. For example, if you want to create a bar graph, you can use GM bar, histograms, GM histogram, box plots, scatter plots. Right? So if you want to take a look at a big picture of using ggplot2, you can check the cheat sheet website, data visualization of ggplot2. And this is a PDF version. And on this web page, you can see some details in the cheat sheet, but in larger characters, so easier to read. All right. So ggplot2 allows you to add multiple layers of GMs into the same plot, into the same coordinate system. As we learned last time, ggplot function will open a coordinate system, and you can choose to add layers of GMs to it. So for example, if we want to overlay this smooth curve on the scatter plot, we can just add another GM to the original one. So we'll first add a layer of point and then add a layer of curve or line. However, if we examine this code, you see some duplication. You see the mappings are exactly the same, right? To avoid this kind of duplication, we can choose to move this mapping into the ggplot function part, as I said last time, right? So move it to the ggplot part. And then you can, we don't need to specify any arguments in the GM part anymore, right? But you still need a pair of parentheses when you call them. And this is a global option, okay, or argument or global mapping. And global mappings will in effect in all of the layers of GMs. However, you can choose to override it in local mapping options. For example, we create this so we still choose to put the mapping in ggplot, this part, and then we want to map a categorical variable drive to color for the points only. Then we can add a mapping argument in gem point. So then you see this plot. See, we use different colors to display different drive categories. So red is four wheel, and green points are corresponding to front wheel, and blue points are corresponding to rear wheel. However, you see, since this mapping is local in gem point, it does not have any effect on the curve. So the curve will still have only one curve. So we fit a global curve for all of the points, but we choose to use different colors to show different drive categories. Right? And apparently, this one is sort of like an extension of the mapping option. It did not override anything because there is no conflict, right, between these two mappings. So it's kind of like an extension. You can also choose to override the global option. if you specify a different X and different Y here, it will work, I believe, or something else. Okay, but it will override the global option. All right. Next. Of course, we can add local mapping for the smoother too. For example, we can map the drive variable to line types. Then ggplot2 will automatically use different line types for different categories of drive. So you see, this is dotted. Dotted is for front wheel, and the solid line is for fore wheel, and this one is for rear wheel. Okay. And of course, this is not really good because we use sort of different GMs, different visual cues to show the same variable. Right? In the points part, scatter plot part, we map drive to color, but in the line part, we map drive to line type. This is not very consistent. A better option is just directly map drive to color in the global mapping part. Then you see they are more consistent. Yeah. And also notice that whenever we map a categorical variable to a visual cue, legends will be provided automatically for us. So this is also, yeah. So this one is also, you see, colors and line types are also shown here in the previous example. All right. And lastly, we can add context to a plot. So notice that if we don't specify anything, then by default, ggplot2 will only provide the minimum amount of context, usually just X and Y axis labels and tick mark labels and legends if necessary. But we can definitely choose to add more context. We use the labs function to add context. You can put a lot of different context in this. Labs stands for labels. So for example, we can add a title using the title equals function. We can add subtitle. We can also add a caption. The caption will be at the bottom of the plot. So caption is here. And just don't forget to use comma to separate these arguments. And notice that in this plot, I map class to color instead of drive class. Class has 7 categories. But I didn't map class to color in the line plot, like in the smoother plot. And instead, I specify SE equals false. SE stands for standard error. So by default, it is true. So a 95% confidence band will be provided for us automatically. You see 95% confidence band. Right. But if I don't want to show it, I can just set SE equals false. And we can also add X and Y. We can also change X and Y axis labels. So the argument are just X and Y. X equals and Y equals. You see, instead of using the original variable names, we can give a long character string to explain the variable. We can also add the units of each variable to it to make the plot better in conveying information to your readers. Okay, so you can change X and Y labels. So notice that I still put these in the labs function or layer. And legends will be provided automatically whenever you map a categorical variable to a visual cue, but you have the option to omit legends. You can just say show.legend equals false, then the legend won't be shown. And these two functions, gem_text and gem_annotate, can also be used to provide some textual annotations on the plot. So basically, gem_text can you can use it to add any text anywhere in your plot. You can just specify the coordinate that you want to add the text and also the sentence or the text you want to add. Right? And annotate similar, right? Perform similarly. So you can add, for example, arrows, some other signs to a plot. All right, now let's move on to the next topic. We'll talk about logarithmic scales. Take a look at this data set, the diamond data set. I think it is built in ggplot2. Okay. So this data set contains information about 54 diamonds, 54,000 pieces of diamond. And the variables are price, carat, which is the weight of each piece of diamond, and color, clarity, and cut of each diamond. Right? So it's a quite big data set with 54,000 observations. Right? So suppose we are interested in the relationship between weight and price of the diamond. I want to know what relationship we have. Right? We can create a two-dimensional bin plot to show the relationship. Right? So start with ggplot. I specify the data set and the basic mapping. X is equal to carat, which is the weight, and Y is equal to the price. Right? And then add a layer of two-dimensional bin plot. So two-dimensional bin plot is a variation of scatter plot. So instead of showing each observations using points, it will separate the entire data, the two-dimensional plane into grids, okay, somehow like this. So for our data set, it will separate the coordinate system into equal distance, not necessarily squares, like rectangles, right, with the same size. And then it will count how many observations in each cell. And then use color saturation to show the quantity. So for example, you see from the legend, we can see that the larger the count, the lighter the color, which is a little bit counterintuitive, but ggplot2 just is designed in this way. Okay, the larger the value, the lighter the color saturation. So basically, for each rectangle, it will show the count. So see, this one is the lightest. This cell is the lightest, which means there are most number of observations in this cell. Right. All right. So this is a two-dimensional bin plot. It's a good way to show relationship between two quantitative variables if there are too many observations. If you create a scatter plot, you will see a very dark cloud of points. It's very difficult to see the density, which part has more observations, which part has fewer observations. But this one is a good way to show large data set. Anyway, from this bin plot, you can see that there is a positive relationship between carat and price. Right? However, it may not be a linear relationship, right? You see somehow like a curvy relationship. Right? And also, you see that the variation increases as the magnitude of X and Y increases. So this is a sign that the data are kind of skewed. Right? So let's try to take log 10 of both x and y and then recreate the beam plot. So we can directly apply the log 10 function on both weight and price and create a plot. Okay. So now it looks very linear, right? And the spread does not change anymore. So you don't have, if you fit a regression model, linear regression model, you won't need to worry about the constant variance assumption anymore because the variance, yeah, stays similar. Okay. So very good transformation. However, in this graphical display, you see that the x and y variables, the tick mark labels are corresponding to the log transform data. So you see negative 0.4, 0.4, 0.8. So they are not very intuitive anymore, difficult to understand and interpret, right? Because they are corresponding to the log of the original values. So negative 0.4 is actually just 10 to the negative 0.4, okay? And it's definitely a positive number, but it is shown in the log scale, log caret. So a better option is to use logarithmic scale. Okay? So instead of transforming the data manually, we can keep them as their original forms. And instead, we add these two lines, scale x log 10, scale y log 10. Then you see still the data is sort of transformed still. I use log 10, but actually the x and y the xy axes still show the original values of x and y. You see positive values, right? The original values. Although you see the increase in a nonlinear way, in an exponential way. So this is a better practice in visualization. Use logarithmic scale. Alternatively, we can use these two functions, scale x continuous and scale y continuous. And with transform, trans equals log 10 and trans equals log 10. So these two are more flexible than the previous one. Okay, the previous one are only good for log 10, but these two are good for many different transformations. For example, you can use natural log by specifying quote log. You can take square root or you square it. So there are many more options. So this is an alternative way to use logarithmic scale. All right. Now let's talk a little bit more about color scales. So as we have learned last time, this R-Color Brewer package provides some colorblind safe palettes in a variety of hues or groups, right? So let's take a look at the plot. So the first plot, in the first plot, we use regular color option, the default color option. We map drive to color. So for normal people, it's okay, but you see the contrast between among colors is not very obvious. We can choose to use colorblind palettes by specifying this scale color brewer. Don't forget to add plus at the end of the last layer. So we use this to connect the different layers of code. And we can use use set one. Remember, set one is one of the qualitative palettes, which is used for qualitative variables, categorical variables. So you see, apparently now these three groups look more different in colors, much more different. Okay, so this is kind of colorblind safe. All right. Let's examine this scatter plot again. So this is the original scatter plot between displacement and highway. So can you tell that this plot actually only has 126 points? Okay. But the data set, MPG data set, actually has 234 observations. So it turns out that because of rounding, the data are kind of coded in grades. So there are a lot of repeated values. And consequently, each point in the plot may represent multiple points. They overlap with each other a lot. So from this scatter plot, you cannot tell the density or the mass of points, right? So one way to resolve this problem is to add an argument called position equals jitter. If you specify this argument, then ggplot2 will automatically add a small error to the coordinates, to x and y at the same time. So it's kind of jitter a little bit. Then after that, you can see the true, sort of not exactly true, but you can see the sort of the density of observations in the scatter plot. For example, there are more observations over here than over here. From the previous plot, you cannot tell any difference in density. In this plot, it's more obvious. And because this is a very useful operation, ggplot2 also provide a function called GM jitter. So this is exactly the same with this GM point with position equals jitter. To be honest, a better practice or better choice is to change the transparency level of the points by setting the transparency parameter alpha. For example, if by default is equal to 1, so all of the points are 100% solid. If you set it to be, for example, 0.5, then you can tell the difference. If there are more observations on one point, then it will look darker. And if there is only one point there, it will be lighter. That's only 50% of the solid shade. Right? So that will be a better, I think that will be a better option because you will not twist your data. Right. All right. Any questions so far? So now let's move on to the last session. We talked about, so now in this section, we will talk about coordinate systems, a few examples of different coordinate systems. And lastly, statistical graphical displays. Ultimately, the goal of graphical display is to understand your data, to explore your data. But for different data types, we should use different graphical displays, and different combinations of data types require different types of graphs. So in this part, we'll talk about different cases. So first, take a look at coordinate systems. In ggplot2, there are 3 of them. By default, Cartesian system. We also have map system and polar system. So for Cartesian system, you have the option to flip the axes. For example, we create, so now in this, we still use the MPG data set. We want to create a box plot for highway fuel efficiency, highway MPG. And we want to compare the highway fuel efficiency among different classes of cars. Then we can let X be class, Y be highway, and then create a box plot. So it will be a side-by-side box plot. You can compare the distribution of highway fuel efficiency among different classes. Apparently, So these two, compact and mid-size, have relatively the highest highway fuel efficiency if we use median as the standard, and median is the bar, right? And we can also see that this subcompact has the largest spread, etc. If we only have a few categories in the categorical variable, then this vertical box plot is okay. But what if we have like 20 categories, 30 categories, okay? Then it might not be very convenient to use a vertical box plot. In this case, we can choose to flip the coordinate system. Just add a line, co-alt flip. Then you see we have this plot. Right? Everything. So X becomes Y, Y becomes X. So notice that in this chunk of code, I first save the result of this box plot in G, as a G, and then I type G with this. And then take G and add this co-alt flip function, you can flip it. Right. I didn't save the result, by the way. G is still like this, okay, but you can twist it a little bit. And also, if sometimes the X tick mark labels are very long, suppose you have very long text strings for each class, then it will be better to use a horizontal box plot, because then you have more space for each tick mark label. It will be easier. All right, so this is for Cartesian system. You can flip the X and Y axes. And next, let's see an example of map coordinate system. Again, our class is not focused on geographic data like spatial data. So we will just use one example to see the importance of using the correct map system for this geographic data, right? Geographic data. So let's see, we will load this package called maps. So this one contains some information about different countries and counties in the world. In the US, we have county data, geographic county data. So let's load the data about New Zealand. So this map data function is contained in this maps package. And call it NZ. And then let's first create a regular polygon plot. A geometric GM polygon will create a polygon plot somehow like this. Right? X is longitude, Y is latitude, and group equals group. So this group is a categorical variable which defines a small unit of data. The unit maybe is about an island, or yeah, it's a kind of an area of observations. And then add a layer of GM polygon, and fill is white and color is black. So we have this. Right? So this is how it looks like the map of New Zealand looks like if we use the regular Cartesian system. Right? However, if we use the correct coordinate system, which is the map system, it looks like this. Right? So you see the difference between these two. Right? So this is the correct look of New Zealand. This is not the correct look. Okay, it's expanded and twisted. So this example shows you that it's very important to use a map system for geographic data. All right, next one is polar system. Yeah, again, in the polar system, we also use two coordinates to show the position of a point. So there are two coordinates. The first one is called the radial coordinate, or simply radius. So for example, for this red point, the radius is this, the length of this. Right? And the other one is called angular coordinate or just polar angle. So this is the angular coordinate. And then let's see how to create a pie chart using ggplot2. Notice that ggplot2 does not have a specific gem for pie charts, right? I don't know why. Probably the author doesn't like pie charts at all. And so there is no function corresponding to pie chart directly. However, you can create a pie chart using a bar graph, transform bar graph. So let's first do something that's, we would use a data set called mtcars. So this is a built-in data set in R. You don't need to load it or import it or download it. So we first will convert cylinder to a factor because we will use it to create to separate the data. We'll create a bar graph for cylinder. It was coded as a numeric variable. But I want to treat it as a factor. And then we first create a bar graph. X is equal to cylinder and fill equals cylinder and create a bar graph. We have this. This is not necessary for a regular bar graph because we have X tick mark labels. We can differentiate these three categories. Right? However, this will make it look better. We'll use different colors to show different categories. Right? So this is a basic bar graph. Right? Then the next step is to change some arguments. Let X be 1, the factor of 1. Right? Somehow like this. It's a 1. Right? So 1 value for X. And then fill equals cylinder. So this will actually map cylinder categories to different colors in the same bar. So this is a result. Right? You have 1 bar with 3 colors. Right? And of course, the height of each part is corresponding to the proportion of each category. Right? So it's a stacked bar graph. And also gem bar width equals 1. So the width of this bar is 1. This is the intermediate result. Okay. And finally, we will add a coordinate polar. Right? So we will, instead of using, so by default is a Cartesian system, right? But you can add this to change it to a polar system. And theta equals y. This theta is corresponding to the angular coordinate in a polar system, and we map y to theta. What is y? Y in this plot is, you see, originally is corresponding to the height of the bar. Consequently, in this case, it's corresponding to the height of each part of the bar, the category proportions, right? And then we omit the X and Y labels, omit them, because in the polar system, it doesn't make sense to use the original labels anymore. And then we have this result. So it's a pie chart, right? Quite a lot of work. And there is a pie chart function in base R, right? But it's very basic. It does not look very nice. And we will see another way to create a pie chart a little later today too. Anyway, this is a way, right? And this is how we change the coordinate system. Just add this, like coord underscore polar. Change it. All right. Now let's move on to statistical graphical displays. So this slide shows you a big picture of the class that for different variables and different combination of variables. Okay. For one continuous numerical variable, we can create a histogram, a density plot, box plot, and QQ plot, and area and frequency polygon. Okay. And in particular, QQ plot is used to check the distribution of some sample data. So it's kind of special in this group. For one categorical variable or one discrete numerical variable, we can use a bar graph, a pie chart, or Cox-Cum plot. So this is a variation of a pie chart. And for two numerical variables, we are interested in the relationship usually, right? So we can use a scatter plot or a contour plot. So this one will show the joint distribution of the two numeric variables and also two-dimensional bin plot. We have seen this in the diamond example, right? We use color shade saturation to show the density, right? So that is actually a three-dimensional plot. The third dimension is shown using the colored saturation. And then two categorical variables, we can use a tile plot. Tile plot is very similar to two-dimensional bin plot. So actually in ggplot2, you can use these for both cases actually. And the next one is stacked or dodged bar graphs. And last one is count plots. And the last group is one categorical and one numeric. So basically grouped numeric data. So you want to examine the relationship between one categorical variable and one numeric variable. We can use side-by-side box plots. We have seen this already. And we can create a violin plot. So violin plots are similar to side-by-side box plots, except for we use a violin shape for each category of data. And last one is frequency polygon. All right, let's start from the first group, the one numeric variables. We definitely can create a histogram. Whenever you have any numeric variable, the first action probably is to create a histogram to check the overall distribution of the sample data. So we can use the ggplot function to create a histogram. Right? So notice that I use a data set called SAT 2010. So this one contains some information about SAT scores in 2010. There are some different scores. One of them is the math score. So notice that I save this in G. Right? G is just a coordinate system with the data stored and also the x variable specified. Right? No gems yet. Okay? No geometric object specified yet. Okay? And then I add a layer of histogram. Okay? And then you see this is so this line print out this plot, create this plot. So this is a raw look of the histogram using ggplot2. Right? It's not really good because even there is no borders for each bar even. Right? And also automatically this message is printed for you. Right? Start bin using bin equals 30. So this is a default number of bins that is used for our data, 30 bins. You can choose to change, you can change it. Okay? For example, if you think there are too many bins, you can change it to 20 or 15, etc. You can also change the bin width. Okay? Essentially, you can just, if you have larger bin width, then apparently fewer number of bins. And the second plot, I still take G and then add a layer of density curve. So this one is showing the empirical density curve using kernel smoother. So it will show you the pattern of the distribution. So density curves, empirical density curves are also useful for showing the distribution of numerical variables. And as we have learned, we can change the number of bins. For example, we can use fewer bins, so 15 bins, then it looks like this. And we can also change the bandwidth in the density curve. So if bandwidth equals 5, you see some more patterns in it compared to the previous one. See, no detail at all in this one. But if you change bandwidth equals 5, right, basically we use a smaller bandwidth. So we have this. So for more details, you can type question mark the function name to see it. Of course, you need to first load tidyverse package, and then you can tap this to see the documents of these two functions. Yeah. So for all ggplot2 functions, these parameters have some sort of optimal values, right, calculated for your data. If you omit these arguments, the function will choose the optimal number of bins, optimal bandwidth for you. You can change it. So namely for different data sets, the optimal number of bins and bandwidth might be different. Pay attention to that. And you can also overlay an empirical density curve over your histogram. Just pay attention that you see from these two plots, the y-axis for the histogram by default is corresponding to the count, right? Bin count, the number of observations in each bin, right? So it's on an integer scale, but the empirical density curve, you see they are kind of like proportions or probabilities, right? They are definitely on different scales. They don't match, right? So if you want to overlay an empirical density curve on a histogram, make sure that you let them have the same scale for the y-axis. So that's why to create this plot, I let y equals density. Y equals density. But in ggplot2, you have to use this kind of syntax after underscore stat, parentheses density. So what is after stat? So this is a statistic that is calculated during the process. Okay, it is stored in the background somewhere. Okay, you can extract them by calling this after underscore stat and density. There are other options, for example, count or proportion. Okay? But if we want to make the histogram and the empirical density curve exactly match with each other, we should use density. Okay, and then we can have this plot. And notice that there are some other functions of other arguments you can use to make your plot look better, right, to improve your plot. For example, I can change the color of the bars using the fill argument, not color. Right? The color argument will change the border color and not the inside of it. Right? And color is the border color. I make it white so that we can see they are separated. And then alpha is used to adjust the transparency level of the bars. Okay, so usually, if you put the histogram in the background, you want to make it lighter. So that's why alpha equals 0.5 is 50% of the solid color. Right? And then bins is the number of bins. Right? So these are local options in histogram. And then for the density curve, I specify the bandwidth and also the color of the curve, and then line width, and make it thicker. Okay? So these are all available, and there are many more arguments available for you to fine-tune your plot, but I just showed you some examples of tuning your plot. So we're done with histograms and density curves. Okay? They usually go together. And we can also create box plots for numeric variables, of course. And ggplot2 also has this gmbox function. So we have seen this before. We created a side-by-side box plot. But for one numeric variable, we can also do it. So as you know, the box plot will show you the 5-number summary, right? The minimum, the maximum, the minimum, the maximum, first quartile, third quartile, and the median. So you can compare the plot with the 5-number summary we calculated using the quantile function. Okay, by the way, the quantile function in base R will, by default, calculate the 5-number summary for you. Okay? And you also have the option to specify a particular probability. For example, if you add 0.99 in it, then it will calculate the 99th quantile. Anyway, this is a very basic box plot. And next is QQ plot. QQ plots are quantile plots. They are used to check the distribution of your sample data. So after you collect some data, you're not sure if the data set follows a distribution or not, for example, normal or not. So the QQ plot will help you to check it. The ggplot2 also has this gmqqq function to help you to create a QQ plot. So it's basically a scatter plot of what? Of your sample data and the theoretical quantiles of your sample data based on normal distribution. So let me briefly explain this to you because I think some of you are familiar with the underlying theory of QQ plot, some might not. Okay, so let me just briefly explain it. So suppose you have a very small sample with 5 numbers. One, if you order them, they are 1, 5, 15, 20, and 30. Okay, 5 numbers. Then what are their theoretical so what percentile they are? Right? So if we, roughly speaking, 1 is the smallest, okay? We can say it is the 20th percentile. Let's just think in this way. And 5 is the 40th percentile. And 15 is the 60s and 80s and 100. Right? Because for 1, there are 20% of observations that are smaller than or equal to 1 in our small data set, right? So 1 is the 20th percentile in that sense. And 30 is the largest, which is 100 percentile. All of the observations are smaller than this. Okay? And the QQ plot function will find the 20th percentile for a normal distribution with a mean and standard deviation that are same with your sample data. Okay? So it will calculate the sample mean and sample standard deviation for your data set and find the theoretical quantiles of a normal distribution with mean equals x bar and standard deviation of s. Okay? So let's just call them x1, x2, x3, x4, x5. Okay? And then create a scatter plot for your sample data and the theoretical quantiles. Okay? And so if your data is from a normal distribution, then what will we expect to see? We'll see a straight line relationship, right? So that is because you see, yeah. So you all know, so we all know about the relationship between standard normal and the normal, right? So um, suppose Z follows a normal distribution with mean 0 and standard deviation 1, and X is also a normal random variable with mean mu and standard deviation sigma. Then we can standardize X by subtracting the mean and divide it by the standard deviation, and is equal to Z. And now it's standard normal now, right? And if you reverse the process, we can easily find that X is equal to mu plus Z times sigma, right? So X and Z should have a linear relationship, right? If both of them are normal, Z is normal, standard normal, X is somehow normal, I is a normal random variable too. There is a linear relationship. Okay. And go back to our small example. So actually in the QQ plot, if you examine the x-axis label, the tick mark labels, you have -2, -1, 0, 1, 2. So apparently these normal theoretical quantiles are corresponding to standard normal. So basically, you will create, so the QQ plot function will create a scatter plot between your sample data and theoretical Z values, Z scores, right? And if your data is from a normal distribution, right, then they are somehow like these axes, right? And the x-axis is are these Z values, right? If your data is actually normal, then you should observe a straight line relationship, right? No matter what the intercept and slope are, right? We don't care about the intercept and the slope. They are the mean and standard deviation of your data, right? But it has to be a straight line. If your data is from normal, it has to be, roughly speaking, a straight line. So that is a whole theory about it. If you observe a scatter plot that is kind of like a straight line, show a straight line relationship, then your data is from a normal distribution. Otherwise, not normal. So now let's see how to create it. So notice that we first add this GMQQ. By default, it will compare your sample data with normal distribution. Okay? However, you have the option to compare your data with other distributions like F distribution, T distribution, chi-square distribution, etc. You just need to specify one more argument. Okay? They are available, but by default, it will compare with the normal, which is the most common case. Okay? And then we can also add a reference line using this QQ line. So this will add this straight line. Okay? So assuming there is a linear relationship, so this is a straight line relationship between y and x. Right? We can compare the scatter plot, the QQ plot, with the reference line. Right? And you also can change the color of line, the color of points, and also transparency. So all of them are like universal arguments you can use to change visual cues. Right? And I also added X and Y labels to the QQ plot, and also the last line theme xVec.ratio equals 1 will make it a square shape plot. Right? By default, it's a rectangular shape. All right. Yeah. You might wonder, why don't we just put GMQQ line first and then GMQQ. That's because I think only if you put it later, you can change the labels of X and Y. GMQQ has its default X and Y labels, and you cannot change it. You cannot change them. All right, this is all about QQplot. I think it's a useful tool in data exploration, so I spent some time on this. All right, any questions so far? Now, next type of data, one categorical variable. We can create a bar graph. So in this example, we will use a new data set, each called help RCT, is in this package, Mosaic data package. So help RCT stands for health evaluation and linkage to primary care. It contains some data about people who use substances like drugs and their health situation. And so there is one variable called homeless. And homeless is the variable name, and it has two categories, homeless and housed. So one category is also called homeless. We can create a small distribution table for this variable. So we can use this with function, with data set, and then apply a function on a variable. I create a table. So these many homeless observations, these many housed individuals in the data set. And then we can create a bar graph to show the distribution of homeless, this variable. So notice that we let X be homeless and let Phil be homeless too, and add a layer of bar. See, this is a very basic bar graph. If you omit Phil equals, then it will just, both bars will be gray, and it will be in gray color. Anyway, this is a distribution of homeless, a very simple bar graph. And there are ways to tweak your bar graphs. For example, let's take a look at the diamond data set again. Suppose we want to create a bar graph for cut. Cut has 5 categories: fair, good, very good, premium, and ideal. 5 categories. It is an ordinal variable. So let's create a bar graph for it. So instead of using the count, so see by default, the Y variable is corresponding to the count frequency. You have the option to use proportion instead. Similar to the histogram, in the histogram example, we can let Y be the after stat of proportion, right? And then you see the y-axis is used to show the category proportions. And pay attention that we need to add this argument, group equals 1. Why do we need this? It is because by default, group is equal to the X variable. So in this case, it's equal to cut. Right? Then if we group the data by cut and then calculate the category proportion, then each category will have 100% proportion, right? Because you already separate them and then you calculate the proportion of that category, definitely 100%. Right? So if you omit group equals 1, you will have a plot like this. Okay, all categories have 100% proportion, which is useless, meaningless. And so you have to specify group equals 1, right, to override the default option, which is group equals cut. Group equals the X variable. Right? And you can also change the color of the bars to still blue. So this is one way to adjust bar graph. So usually we want to show proportions instead of counts. And we can also specify the y-axis manually. We calculate the proportions manually. For example, we can let y be after stat count divided by sum of after stat count. So basically ni divided by n. So that is definitely the proportion. So of course we have after stat proportion. We don't have to do this, but this example just shows you some other possibilities. So in a bar graph, you have the option to specify how the y variable is defined. Right? You can use any quantity. Right? You can calculate by yourself. Right? As long as the quantity is available in the after stat group. Right? All right. Next. Yeah. So by default, the stat argument in GMBAR is the count. If you don't specify the y variable, then stat will be the count. For example, in the very beginning, you see I didn't specify y, right? I only specified x. And the count is calculated automatically for us. And the counts are used to show the height of bar. It is used to define the height of bars, right? So that is underlying stat, okay? Equals count by default, okay? For bar graphs and also for histogram. And you can change this default behavior. For example, suppose I don't have raw data. I have a summarized table like this. Okay? So two columns, cut, category, and the frequency. So since frequency is already available for us, we don't need to calculate it anymore. Okay? So in this case, you see the data set is demo. X is cut. Okay? Ignore this first, read other thing first. Okay? X is cut, and y is equal to the other variable frequency. Okay? So this is x, this is y. Okay? And because we already have those calculated frequencies in this table in our data, we don't need the program to calculate the count for each bar anymore, for each group of x anymore. Okay? So we need to specify stat equals identity, which means it will be just the y variable we specified. And then we'll have this plot. Okay? And what about this? So this one give you the option to order your bars according to some quantity. For example, I ordered the bars, the cut variable, by the frequency, by default in ascending order, from the lowest frequency to the highest frequency. And then we have this result. So this example shows us that if we have summarized data, like summary table, and we already have some value we know we will use to define the height of each bar, then we need to specify stat equals identity to avoid counting the frequency for each category. If you don't specify that, then the count will be equal to 1 for each category, apparently. Right? And all the bars will have the same height, I think. All right. Alternative way to create bar graphs. You can also use this GM column to create the same plot. So GM column and GM bar are kind of parallel in ggplot2. They're essentially the same thing, but GM column it focuses on the counts, right, of each column somehow. But you can use it to create a bar graph. So, all right. Next, Cox-Com chart. Okay. So this is a variation of the bar graph and also similar to pie chart because it uses the polar system. Right? So let's take a look at this example. So we will create a plot for cut again. Right? To create a Cox-Com chart, we will first create a bar graph. Right? But this is not a traditional bar graph because notice that there is no space between any two bars. Right? For regular bar graphs, there is some space between any two bars. Right? To show that the categories are not continuous and it's not like in a histogram, all the bars are together, right? No space. But in bar graphs, there should be some space in between any two bars. Right? So let's see what we did. So X equals cut, fill equals cut. So we'll make them have different colors. Okay? And then width equals 1. So this will, I think this will get rid of the space in between any two bars, right? So get rid of the space. Because in the final product, we don't want to have any space in between the slices, right? So that's why we get rid of the space. And then this part will make it a square shape, right? And get rid of the labels of X and Y. And also get rid of the legends. Right? So by default, it will print out some legend here. And then save the result in bar. So bar looks like this. Sort of similar to a regular bar graph. And then just need to add co-odd polar. And then you see this kind of, so we get this plot. And we change the system from Cartesian to a polar system. So it's kind of a combination of a bar graph and a pie chart. Yeah. However, it is different from a pie chart. Can you tell what's the difference between this plot and the pie chart? Anybody?
In a pie chart, it's the proportion of the circle is the value that we're looking at, and here it seems to be like the size of the triangle or the radius.
Exactly. Thanks. Yeah. They actually use different visual cues or quantities to demonstrate the data, right? In the pie chart, we use angle to show the proportion of each category. But the radius stays the same for each slice, each category. But in the Cox-Com chart, the angles are the same, actually. If there are 5 categories, each one will be, the angle will be 360 divided by 5. They all have the same angles. However, the radius are different. We use radius to show the proportion of each slice, each category. Right? The radius is corresponding to the height of the bar. So that's why. Right? It's kind of a variation of the bar graph and also the pie chart. Right. Yeah. Lastly, a pie chart. As I said, we can actually create a pie chart using base R functions. And let's see. Yeah. Yeah, this one actually still uses a ggplot function. So we first summarize the data. Suppose we want to create a pie chart for cut again. So we create a little data frame. So first create a table. I call it cut table, and then use the data.frame function to convert it to a data frame. And also we add column names. So this is the data frame we have, two columns, cut and count. And then let's create a pie chart using ggplot2 again. But now we're not dealing with raw data. We are using a summarized table. So specify the data set, the data frame, cut df, right? And specify the mapping x equals nothing, right? Only y variable, right? Which is the count, and fill is equal to cut. So then, so this is basically GM_bar, same thing, with width equals 1. So this part will stack all of the categories in one bar, and then use a polar system, right? And the theta equals y. Theta is the angle. And then we'll create this plot. We can also fine tune this plot. So this is G, a basic bar pie chart. We can adjust it a little bit more to make it look better and add more information. So you see by default, the counts are outside of the circle. Right? And we also have X and Y labels, which are not necessary. So we can first do this plus CM void. So this will, I think this will get rid of the background color. And then add some text using GM text function. So label equals count. So this will, so these are the labels, right? The count will be used to label each slice in the pie chart. And position equals position stack, vertical adjust equals 0.5. This means I will put them in 50% of the radius, right? So this is the whole radius is about 50% of the radius. So in the middle of the slice. And then get rid of the X label, the Y label, and fill equals no. Yeah, I'm not sure what this is about. And lastly, use set2. Right? In color brewer, set2 is the second qualitative palette in the second group for qualitative variables. So it looks nicer than the original one. I think the colors look better. And you add some details. Apparently, you can do something else. For example, add proportions instead of count into the slice. Right? Anyway, it's quite difficult to create a pie chart using ggplot2, and you probably need to use a lot of code to create a pie chart. All right, I think we can stop here. So last time we talked about graphical displays for one numeric variable and graphs for one categorical variable. So today we'll start from this case, two categorical variables. We want to study the relationship between two categorical variables. Okay, and so let's still use the data set about homeless people who use substances. Let's consider a different categorical variable, substance. And this variable has three categories: alcohol, cocaine, and heroin. Three drugs. Alcohol is not a drug. Substance. And we already have one categorical variable, which is homeless status, two levels, homeless and housed, two levels. Let's try to display the relationship, show the relationship between homeless and substance. Ideally, we can create a three-dimensional bar graph to show the relationship. So the first two dimensions are corresponding to the two variables, and the height of the bar will show the count in each combination of levels of the two variables. However, usually three-dimensional plots are criticized by researchers, statisticians, um, mainly because human eyes are not really good at reading or understanding three-dimensional plots. Okay. So instead, we can create a flattened version of the three-dimensional bar graph. Namely, we can use color saturation to demonstrate the third dimension, which is the count. Okay. So last time we actually talked about 2D two-dimensional bin plot. Okay. So this one is similar, but this is for categorical data. Okay. And there are some other differences. Okay. Let's take a look. First, we use the width function to create a joint table for homeless and substance contingency table for these two variables. So homeless status and substance, and the cells contain the counts for each combination of levels. For example, 103 people in the sample data set are homeless and they use alcohol. So this is the joint table. Now let's see how to create a tile plot. So take the data set. So in this chunk of code, we actually use some operators like this, percent greater than percent. So this is called a pipe operator or pipeline operator. We will talk about it in more details in the next module, data wrangling. But for now, let's just try to use it first. Okay, it's kind of like an operator that can connect different commands together. Okay, and the order is from top to bottom and from left to right. Okay? So let's take a look at this. Take the data set and group the data by substance and homeless at the same time. Okay? Then we summarize the data. Okay? We create a new variable called count, which is equal to the number of observations in each combination, in each small group, created by substance and homeless. Okay, for example, so this step will calculate these six numbers in a table somehow. Okay, we call it count. And then this variable will be available for us to use in the next step. In the next step, we will create a plot using ggplot. In the mapping part, okay, X is substance, Y is homeless, and fill is equal to count. This count is created in the last step. And then lastly, we add a layer of tile plot using gem tile. So this is the plot. So it's very similar to the two-dimensional bin plot. You see, by default, it will use this kind of blue color shade, and the lighter the color, the larger the count, actually. And so there is at least one difference. You see the third dimension, fill equals count. This variable has to be calculated, or it should be available before we call the function, we use the function, right? But when we do the two-dimensional bin plot, the third dimension is corresponding to the sort of it's also count, but we don't need to calculate it by ourselves, right? It's automatically calculated in the background of the function. Okay? So two-dimensional bin plot will automatically calculate the count for us, but tile plot will not. Okay? You have to provide this quantity. All right. Alternatively, we can create stacked bar plots to show the relationship between two categorical variables. So usually the main question is, are these two variables related or not, or associated or not, or they are independent? Right? So this type of plot can help us to answer that question. So let's see how to create a stacked plot. So first, ggplot specify the data set. X is homeless, and we map substance to fill, which is the color of the bar. So this will separate each bar to three segments. Each one is corresponding to one substance, right? And then add GM bar. So we have this plot. This is called a stacked bar graph. The y-axis is corresponding to count by default. However, although we can see some differences between the two bars, so namely we want to know if the distribution of substance is the same between the two groups of homeless status. So we want to know if the distribution of substance is the same. So although we use count, we can still see there is some difference, right? For example, the cocaine. So this segment is smaller among homeless people compared to the segment in housed people. A better way to create this stacked plot is to use proportion for the y-axis for the height of bar. We just need to add this argument, position equals fill in GM bar. Then you see that the height of the bars will become 1 for both bars, and also so the height will be corresponding to proportion. And we can easily see that this plot can help us to sort of compare the conditional probability of substance given homeless, right? Because each bar has the height 1, which is 100%. For example, you see for homeless, this group, 50% about 50% of people use alcohol. It's very clear from 50 to 100, so 50%. But among housed people, only about 30% use alcohol. And you can see the difference very easily. The difference is very obvious because we make them have the same height. So this is a good way to answer questions such that, for example, is there a higher chance of using a heroin if the person is housed as opposed to being homeless? If you compare these two, heroin, yes, right? If it's housed, the proportion is higher, is bigger than homeless. Right? So we are essentially comparing this probability of heroin given house and probability given homeless. So are they equal or not? So definitely not equal. Housed is higher than homeless. So whenever you want to answer questions about conditional probabilities, you should consider this argument, position equals fill. And also pay attention to the definition of the event and condition in the question. So in this case, you see homeless status is the condition, and the event of interest is about substance. And another option is to use a Dodge position. So first create define the ggplot part as G, and then we first let position equals dodge. Then you see this is the bar plot. So we have two sets of bar plots. So for each homeless status, we have a set of bar graph for substance. You can compare the patterns. Apparently, they are very different, right? And this is the one that we got in the last slide. So you can compare these. They are kind of equivalent. They display the same information. From these two plots, we know that homeless status and the substance they use are not independent. Okay? They are related or associated, apparently. If they are independent, we should observe very similar patterns for these two bar graphs, or similar decompositions of the three substances in each bar. All right, so this is another example when the condition is substance. If you want to answer questions such as what is the proportion of homeless whose primary substance of abuse is heroin? So in this case, the condition is the substance, and the event of interest is homeless status. In this case, we should switch these two arguments. So now X is substance, Phil is homeless. Right? In the previous example, we have X equals homeless and Phil equals substance. And you can answer some questions in this scenario when we consider substance as a condition. All right, then let's quickly move on to the next topic. We can also use bar graphs to show ordinal data or discrete numeric variables. Discrete numerical variables are numeric variables, but there are only a few distinct values. For example, in the MPG dataset, the cylinder variable is a discrete numeric variable. It only has 4 levels, 4 distinct values, 4, 5, 6, and 8. And there is no 7 in between. Okay, so this is not a continuous numeric variable. In this case, so this is a frequency table for cylinder, only 4 levels. If we just directly create a bar graph using this variable cylinder, we will have a bar graph like this. So you see, there is so the level 7 is reserved, although there's no data points in this group or for this value, but still the bar graph will leave an empty space for it. That is because it considers cylinder as a numerical variable. It thinks they're kind of like not something is missing. It's just that no observations are observed in this in this interval, but it is still a valid value. Okay? However, we know that this is not a valid value at all. Okay? Cylinder can never be equal to 7 in the data set. So a better practice is to first convert cylinder into a factor. And then, so see, X is equal to S dot factor cylinder. And then it will not, it will only consider the available values in the cylinder column. It will not consider 7 or other values. And then we have a bar graph like this. Okay, so this is more appropriate for discrete numeric variables. Just pay attention to that. Yeah. And then let's move on to the next group of data. We have one numeric variable and one categorical variable, or 2 categorical variables. We want to study the relationship between 1 or 2 categorical variables and 1 numeric variable, grouped data. For example, we can create a side-by-side plot for for PCS in the homeless data set. PCS is physical component score, which are some numeric health measurement for those individuals in the data set. So the lower the score, the worse the status, the health status of the person, those people. This is numeric. We want to compare the distribution of PCS among different substances and also homeless status. We have two categorical variables here. We can show them at the same time. So let X be homeless and Y be PCS. Okay, so we have a vertical side-by-side box plot and add a layer of box plots. And finally, we can use the facet wrap to add substance. So create a panel for each substance. Then we have this side-by-side box plot. So it looks very neat, right? And you can have some observations or have some conclusions from this graphical display. For example, within each substance, you can compare the PCS distribution for homeless and housed people. So for example, housed people have higher median than homeless people, which is intuitive in general. And also in the cocaine group, the medians are similar, but still housed is slightly higher. And for heroin, median is higher still. And you can also compare their spread by comparing the range and interquartile range. Range is max minus mean. Interquartile range is Q3 minus Q1. Okay. All right. So this is a side-by-side box plot. A variation of that plot is a violin plot, using the Gin-Violin function. So this is a very basic look of a violin plot. You have the option to change the colors of these violins. One advantage of a violin plot is you can actually see the kind of the density of observations in each group. The wider the wider the area, the more observations in that area. Okay, we can see different shapes, but we cannot tell where the median is. It will not show the median by default. And another way to compare different numerical distributions or grouped data is to use frequency polygons. Frequency polygons are similar to histograms. So what is a frequency polygon? Let me show you a simple example. Suppose we have a histogram somehow like this. Then a frequency polygon will connect the peak of each bar in the histogram and connect them together. So for frequency polygon, bandwidth is also a parameter. It determines how big the each interval is. Okay. And one advantage of frequency polygon is they only describe the outline of the histogram, right? No bars. So that if you have multiple groups of data and they overlap a lot, if you create a histogram in the same plot panel, they will overlap with each other. You cannot some of the histograms will be hidden in the background. But if you use frequency polygon, you can see all of the distributions. So in this plot, we use a diamond data set. Let X be price. So this is a primary variable, the price of the diamonds. And we map cut to color. So which means we'll create a frequency polygon for each cut, 5 levels. Okay? And then add a layer of GM frequency freak polygon. Okay? So this looks like this. Okay? And by default, the y-axis is corresponding to count. This is not the same with GM polygon. Last time when we talked about the maps, creating a map, we use GM polygon. The polygons are kind of used to create something like this. And frequency polygons are different. Okay, so they are similar to histograms. Okay? And you can definitely change the y-axis. For example, you can choose to use density instead of count. By default, it's count. Then you make all of the frequency polygons have the same scale for y. They are on the same scale so that you can compare the distributions better. And the last plot is for 2 or more numeric variables. Okay. For 2 numeric variables, usually we create a scatter plot to show the relationship and show the pattern, right? And so now we will take a look at a more advanced version of scatter plot somehow. It's called contour plot. Okay. So this is actually a 3-dimensional plot on a 2-dimensional plane. The third dimension is the joint distribution of x and y, or density of x and y. F, x, y. If the 2 variables are x and y. Right? So we know that if we, for example, x follows a normal distribution somehow like this, and y also follows a normal distribution. Just one example. So y will follow is a normal distribution too. Okay? If we plot them together, if we use a 3-dimensional plot, it will be like this. Okay? So it's like a mountain. Okay? It's like a mountain. And the third dimension is the joint distribution. Just the height of the mountain is the joint distribution, joint density of the 2 variables. And if we calculate them and connect sort of all of the f(x) and y, same value x, f(x) and y together, okay? Then we will have something like this, okay? So these contours are used to show the height of the mountain, okay? So now imagine you project the third dimension, okay, down to the 2-dimensional plane, and then the contours will look like this, in this plot. So the points on the same contour have the same joint density value, f, x, and y. Okay? So we can use this function to create it. Right? So in this plot, we first create a scatter plot. The SAT 2010 is the data set. Right? The 2 variables are math and salary of the teacher, salary of the teacher, and then add a layer of points. I save the result in G. So G is the scatter plot, and then we add a layer of contour plot. So using this GM density 2D, and there is a mapping. We map the level after stat level to color. And by default, it uses the color saturation of the blue color. Again, the lighter the color, the higher the level, the larger the value. So it's indeed somehow like a mountain. So this is the topest. And alternatively, you can create a filled 2-dimensional filled contour plot. Just take G and add GM density 2D filled Alpha is used to control the transparency of the colors. Right? So by default, it used this kind of color palette is the Verdis color palette. And pay attention, the legends were in the opposite in a descending order. Okay, so this is the lowest level purple, and yellow is the highest level. If you carefully observe the value range, right, for each color. So different from here. Here, from lowest to highest, but here from highest to lowest. Just pay attention. So it looks better. Actually, this one looks better. And all right, I think right on time.